7.2, Similarity in Transformations. This is a strange lesson because all the work is done for you. You have to describe it or explain what's happening. So it's kind of a strange one, but it's a good lesson, especially because there's things in here that are critical to the standards. So first of all, it says, is there a composition that transforms and maps ABCD to the second figure of the same student? So Helena and Edwin, can their original figure be mapped on to their new figure based on rotation, reflection, translation, or dilation? So now you have 4. Those first 3 were rigid, so they just move the shape. This last one that we just learned, the dilation, that changes the size of the shape. So you're going to describe those, and you're going to try to use the manipulatives and the tools down here to actually move it. So example 1, graph a composition of rigid motion. So here is the visual, and it says if a line M is represented by the equation x equals -3. So imagine this -3, this line right here, there was a line right there. Okay, at -3, x equals -3. What is a graph of the image? So it's asking you to do 2 things, a composition of transformations. So you look at this, and if we need to do the dilation first, that one on the far right is the dilation. And then we're going to do the reflection. So dilation, this is what it should look like. It is shrinking half the size. So it's reduced in size. And then we're going to reflect across that line, that -3. And so it reflected again. And your conclusion is that the composition is this. The end result is this one. And so basically it gets rid of all the steps in between and just shows you the end result. That is a composition of transformations. Here is another picture. What is the graph? And you're going to try this one, whether it be with this computer program or at home or at school with a compass and straight edge. So you're going to do a translation, moving it 1 in the positive direction of the x and then down 2. And then you're going to do a dilation, scale factor of 2. And you're going to use these tools to do so. Good luck on that. And one more, it says for this, try it. Same thing, you're going to do a rotation 90 degrees around the origin. Okay? And it's positive 90, which means you're going counterclockwise. So counterclockwise, this direction over here, you're going to go this way 90 degrees. And then it's going to be a dilation of 3. Get used to using those tools. It's a really nice practice to get used to using those interactive online tools. Example 2, you're going to describe this. So looking at the visual, you have to figure out how XYZ, that's the pre-image, ended up on JKL. So this is a description. What happened? Reflection, rotation, translation, or dilation. And it's a combination of those things. You just have to figure out in detail. So like in this case, it looks like the whole triangle rotated. So where did it rotate from? You need that point of rotation. How much did it rotate, as in degrees? And then obviously one is bigger than the other. So what was the dilation? And I think when you check your solution, that's what you'll see. So whoa, it goes through all this information and it literally says, oh, yep, it's a rotation from the origin, 180, and a dilation of 2. So you're doing the explanation. I love how these manipulatives, you can see your angle and it shows you exactly how it moves. So you're like, oh wait, right about there. Oh yeah, that's in the right spot. And then if I do a scale factor, as it increases, oh yeah, there's my right spot. So you can actually use these to manipulate and help you on your journey in figuring out this solution. So triangle can be rotated 180, and it's literally the same picture, but then it says, if these transformations are performed in reverse order, so if you change the order in which you're writing them, what happens? Do you think the answer holds true for all things? So if I rotated and then dilated, or if I dilated and then rotated, how will that change? And is that true for all of them or not? All transformations. Example 3 is a similarity transformation. So it is a composition of one of the rigid motions. So it's a dilation plus one of those other 3s, rotation, reflection, translation. So dilation plus one of those rigid transformations. And if you look at this, it actually goes through it. So you could reflect it, you could translate it, and then you could dilate it. And that's exactly what this picture did. So this up here is reflected translated, then dilated. And so it obviously is a similarity transformation because it has the dilation and at least one of the other transformations. So there are some things that you need to know. These are properties of similarity transformations. So reflexive property still works. So if you have like a segment X, Y, and when you translate it, it's still going to be similar to X prime, Y prime. And this symbol right here, that squiggly line, that means similar. So it doesn't necessarily mean equal. In fact, the only time it would be equal or congruent is if the scale factor was 1. So that similarity means there's a change in the scale factor. So something is similar to something else if there is any kind of transformation. It will be similar. Okay? And then the symmetric property works if some shape, like triangle X, is similar to triangle Y, then triangle Y is still similar to triangle X. So the similarity properties still work. So the symmetric works even if it dilates in size. And the transitive property. If you have a triangle similar to another triangle, and this triangle is similar to a third triangle, then basically you skip the middleman. So this original is similar to this. So if A is similar to B and B is similar to C, A and C are similar. You're getting rid of that middleman, and that is the transitive property. And that still applies in rotation, reflection, translation, and dilation. Okay, you're going to describe this. What is the change? What is happening to these figures? What kind of similarity transformation? And again here on this example 3, you are still describing the transformations. Now you're going to determine what's happening with an application problem. Can the artist copy her sketch to cover an entire wall covering 15 feet high by 20 feet wide? So her wall mural is similar. So if you had this drawing, this sketch mural, and you want to make it a mural, will it fit? So let's do some math here. And there's a couple different ways. In fact, I think the book does it a different way, but I'm going to show you. If I have 14 by 11, so I'm going to say 14 by 11, I need to know what that scale factor is of considering my base to my height. Remember, I said you can change the ratios in another video as long as you're consistent. So I'm going to say base to height. That's going to be my scale factor. I'm comparing within the figure. So if I take 14 and 11, I need to figure out if that's going to be the same as, I'm going to take the longer side, so that would be the base, and the height would be 15. Is that the same as 20 over 15? And even though one is doing inches and one is doing height, I can still do this math. So when I look at these numbers and I put them in a calculator, like 12 divided by 15, I'm like, okay, it's 1.3 repeating. And if I do 14 divided by 11, and I'm just literally plugging them into the calculator, does that equal 1.27? And the 1.27 is repeating. I'm like, no, those aren't the same. So obviously this mural that's on here will not be able to fit perfectly on this wall into a mural that covers the entire wall. The next part of this problem I really like because it's taking, well, okay, it doesn't cover the whole wall because the scale factors are not the same. That's why we did those ratios. Are those ratios the same? But now it says, suppose the artist cuts 2 inches from the width of her sketch. So instead of taking this 14 by 12 or 14 by 11, we're going to take this 14 and cut that by 2. So I'm going to say that's 12 by 11. So do it again. So do the base times height, or I'm sorry, do the base compared to the height. Will that be the same as the base compared to the height of the wall? And you just work this out. So the base of the painting is 12 inches. The height of the painting is 11. Is that the same as the base of the wall, 20 feet, and the height of the wall? Grab your calculator, try to figure that out. Does it fit? Identifying similar circles. Now this is what's crazy. Circles have a special property. They really only have one dimension. It's the radius. So like you think of a rectangle or a triangle or any other polygon that you can think of, there are at least, well, 2 dimensions. If it's a 3-dimensional thing, then they would have 3 dimensions. But think of all the 2-dimensional things. You have a base and a height. a length, and a width. You have two things to deal with. Circles, one thing. That's a radius. So you need to write a proof that any two circles are similar. But just think about this. If I multiply, and I'll get the pen out, if I multiply this scale factor, or r, by some number, and I'm just going to say number, some number, I could use anything to get another radius, because I could just divide s divided by r, and that would give me the number I need to multiply by. Okay. Now, if I wanted to go the other way, and I want to say, okay, I want to prove that s is corresponding, or a dilation of r, I could do the same thing. So what's my number that I had to multiply s by to get r? Again, s compared to r, I can still get that number, but you would be dividing, or I could say the new over the original, and then that way I would get the fraction. So all circles, no matter what, because there's only one number that you need for the scale factor. There's not multiple dimensions that have to increase or decrease. There's only one. Therefore, all circles are similar. Concept summary. Here's the big picture. So words, similarity transformation is putting one or more rigid motions with a dilation. So that's making a combination of rotation, reflection, and translation with that dilation. Two figures are similar if the similarity transformation maps them. So if you can take some kind of rotation, translation, reflection, and a dilation and map a picture onto another picture, it is similar. All circles are similar no matter what, because they only have that one dimension. And then here's some diagrams showing some examples of similarity transformations, or a composition of those. And all circles are similar. I hope that helps.